This is lesson 4 in unit 9, and today we're going to talk about solving motion problems using parametric and vector valued functions. In our last lesson, we looked at finding derivatives and dot products of vector valued functions. We've used both component form and linear combination form, so you can be familiar with either of those notational marks. In this final lesson, we're going to use the concepts of vector-valued functions and parametric equations to look at the motion of an object along a curve. As a particle moves along a curve in the plane, we're going to define that vector, that position vector, again using r of t, with the horizontal movement as x and the vertical movement as y, both of those being functions of time. And by doing this, we can use the derivatives of r of t to describe the velocity and the acceleration of the object. And here in this screen, we're going to define velocity as r prime of t, where we've taken the derivative of the horizontal component and the derivative of the vertical component. And speed is absolute value of velocity, which uses the distance formula. We saw that in our last lesson. Acceleration is the second derivative of our vector valued function, and then the distance formula is simply taking the definite integral from some point A to B using the velocity. So let's jump in. The derivative as a tangent vector. In this graphic, we see that the derivative vector, which is r prime of t, points in the direction that is tangent to the path being traced by the position vector r of t. And here's our position vector. This is our position vector r of t right here. And this is our velocity r prime of t. So we know that the limit as the change of time goes to 0 of the change in r over the change in time is our difference quotient. And as the change in time approaches 0, delta r over delta t has to approach the velocity vector that's shown here in red in our figure. And velocity and acceleration are vectors, and they have both direction and magnitude. So let's explore some of these concepts. In example 1, if an object moves along the plane curve, C, described by the vector function r of t given here, we want to find the rectangular equation that describes the object's motion. So in linear combination form, the x motion is described as 3 cosine of t, and the y motion, or the vertical motion, is described as 2 sine of t. So if we divided both sides here by 3 and squared that, we would have x squared over 9 would be equal to cosine squared. And similarly here, y squared over 4 would be equal to sine squared. And by treating these two like a linear system, we could add them together and they would give us that rectangular equation, x squared over 9 plus y squared over 4 is equal to sine squared plus cosine squared, and that's 1. So we have an ellipse that is centered at the origin and has a length of 3 on the horizontal and 2 on the vertical. In part B, we want to find the velocity vector, speed, and the acceleration vector. Not sure where that came from. So the velocity vector, v of t, is r prime of t. And using our original, that would be negative 3 sine t in the horizontal component and 2 cosine t in the vertical component. So I'm just taking the derivative of each of our pieces up here, -3 sine and 2 cosine. The speed would be the absolute value of our velocity, and that's going to be 9 sine squared t plus 4 cosine squared t under the radical. There's our speed. And acceleration is going to be the second derivative, r double prime of t, and taking the second derivative here, that's going to be -3 cosine t in the horizontal direction and -2 sine t in the vertical direction. And once again, if you would rather write the component form, you can write the component form using our brackets like such. So it just depends on which method you prefer, whether you write linear combination or component form. In part C, they're wanting us to sketch the graph of the path and use arrows to show the direction. So if we started at 0 and the vertical was 2, the horizontal was 3, so we have a long skinny ellipse like such, and putting arrows on the pathway that would go counterclockwise around from 0 to 2 pi to show the full rotation, and then drawing sketch the velocity and acceleration vectors at the point 3, 0. So our velocity vector at 0, if you go back to -3 sine of 0 plus 2 cosine of 0, then our velocity vector is going to be 3, 0. So that would be our velocity vector at 0. On part D, I'm going to show the work for that. So the velocity at time equals 0 is r prime of 0 3, 0. So r prime of 0 is -3 sine 0 in the I direction and 2 cosine 0 in the j direction. So the velocity at 0 is 2j. So that, whoop, I drew my vector too big, 2j. So we go here. And then acceleration is -3i, I believe. Let's see. So acceleration at 0 is -3 cosine 0 in the I direction minus 2 sine 0 in the j direction. So the acceleration at 0 is -3i. So we got one vector and another vector, and this is using the point 3, 0. So at the point 3, 0, the acceleration vector is -3 in the horizontal direction. So -3i would be right to there. So the acceleration vector at 0 and the velocity vector at 0 was 2j. Okay? Example 2 says to sketch the path of a particle moving along the plane curve given by r of t is 4 minus t squared horizontally and t vertically. Then we're going to find the velocity and the acceleration vectors at t equal 1 and sketch them on the graph. So for minus t squared in the I plus t in the j is going to be some sort of a sideways parabola heading that way, showing the arrows in the direction, and then the velocity vector would be negative 2t in the I direction and 1j, and the velocity vector when time is 1 is going to be negative 2I plus j, and then the acceleration vector would be negative 2, and the acceleration vector at 1 is negative 2. Need the I on here. And sketching those on our vector at 1, we have negative 2 in the I direction and 1 in the j direction. So when time is 1, we've got 2 and up 1, and the velocity, we've got negative 2 in the I direction. So this is acceleration at 1, and this is velocity at 1, not the straightest line. Okay, I straightened this up. So the velocity at 1 is negative 2 plus 1 on the vertical. So we went 2 left and 1 up, and the acceleration 1 is negative 2 toward the left. So this is my acceleration and this is my vertical, and this is where time is 1. Now, what I didn't show you is I used my calculator initially to draw this graph. And if you go and substitute starting at time is 0, you see that when time is 0, our x is 4 and our y is 0. So that was my initial ordered pair 4, 0. When time was 1, I got the ordered pair 3, 1, and then 0, 2, and negative 5, 3. That's how I knew that I had the parabola going sideways at 4, 0, at 3, 1, at 0, 2, and then negative 5, 3. So you can always make a table if you don't have a graphing utility to do that. For example 3, the position of a particle at some time is given by this parametric equation, and we want to write an equation for the line that's tangent to the path of the particle at the point where time is 1. So the first thing I want to do is calculate the value when time is 1. R of 1 would be 2 plus 3 in the horizontal, and then 1 minus 12 in the vertical. So our R of 1 in component form would be 5, negative 11. Secondly, we're going to find out what the velocity is. So velocity is going to be 6t squared plus 6t in the horizontal direction and 2t minus 12 in the vertical direction. So again, we want the velocity at 1, and substituting 1 here, we have 6 plus 6, so 12 in the horizontal, and 2 minus 12 would be minus 10 in the vertical. So our derivative, dy dx, is going to be negative 10 over 12, or negative 5 over 6. So we have a point, and we have a slope, And with a point and a slope at our given time, then we can write the equation of the tangent line. So y is equal to the slope -5/6 times the quantity x minus 5 minus 11. So our point was 5, -11. That was our vector, and our slope was -5/6. So we have the tangent line, tangent to the path of the particle at the point where time is 1. On part B, we're going to find the coordinates of each point where the horizontal component of the velocity is 0, and we're going to assume positive time. So our horizontal component would be the ith direction. Our horizontal component is 2t cubed plus 3t squared. And we're looking where that horizontal component has a 0 velocity. So the derivative, that would be dx dt. That would be 6t squared plus 6t. We want that to be 0. So factoring out a 6t leaves us t plus 1. And assuming positive time, so positive time, we only have one valid solution, that's 0, since t is not negative time. And we want to find the coordinate of that, so that would be the r of 0 when the time is 0. And substituting back into our original equation, 2t cubed plus 3t squared I gives us 0I. And 0 squared minus 12 times 0 gives us 0j. So 0 minus 0. So we're really at the origin. We have our horizontal component with the velocity is 0 at the origin, or 0, 0 vector. Okay, so we just considered the horizontal component. In this one, you might want to grab your calculator. We're going to need to use some calculations. If we're given acceleration and velocity and position, we want to work backwards to find the position vector and then find the position of the object at time equals 3. So working backwards, we're going to integrate negative cosine t minus sine t in component form, just for simplicity. And that velocity is going to be negative sine t plus a constant, and then positive cosine t plus a different constant. So we did the antiderivative, and they've told us up here the velocity at 0 is 2I. So if you substitute 0 here, we know that the first constant is going to be 2, and the second constant is going to be -1. And the way I figured that out was I took this term, negative sine t plus c sub 1 has to be 2I. So I know that our j term has to be 0. So this is our j term. And cosine of 0 plus c sub 2 has to be our 0 term for velocity to be 2I, comma 0. So that's where we got the c sub 1 is 2, and the c sub 2 is -1. So we don't need that work, just to show you where that came from. And what else do we know? So now we know that r of t is negative sine t plus 2 in the I direction, and cosine t minus 1 in the j direction. We can integrate this, And by integrating, we've got the cosine of t plus 2t and a new constant, we'll call that c sub 3. And then for this piece, we've got the sine of t minus t plus a new constant for the j term. And then back here, they've told us that r sub 0 is j. So one more time, if r sub 0 is j, then we can consider this piece, cosine of 0 plus 2 times 0 plus c sub 3 has to be the 0 term, since our vector is going to be 0i and 1j. So this piece is 0. And cosine of 0 is 1. So 2 times 0 is 0. That makes c sub 3 negative 1. And then this part over here, we've got the sine of 0. The sine of 0 minus 0 plus c sub 4 has to be j, and j is 1. So the sine of 0 is 0. That means c sub 4 is 1. So we know c sub 4 is equal to 1. And then putting all of that together, if c sub 3 is negative 1 and c sub 4 is positive 1, our vector r sub t is cosine, I'm taking that from here, cosine t plus 2t minus 1 in the horizontal direction, and then sine of t minus t, and c sub 4 is positive 1 in the j direction. So we're going to use this position vector. And then what did they want us to calculate? Find the position when time is 3. So this is where we're going to need our calculator to get an estimate, because when time is 3, we're looking at the cosine of 3 plus 2 times 3, that's 6, minus 1. And then the horizontal, that's the horizontal. Then the vertical is the sine of 3 minus 3 plus 1 in the vertical. So let's go grab a calculator and do those calculations to find an approximate position when time is 3. Okay, using my calculator, and you can verify that we have the same results. The cosine of 3 plus 5 is about 4.0100 in the horizontal direction. And then the sine of 3 minus 2 is about negative 1.8588 in the vertical direction. So this is my approximate location of the particle at time equals 3 in linear combination form. If you wanted to write that in component form, it would look like 4.0100, comma, negative 1.8588. So whichever method you prefer. And then our last example is going to deal with projectile motion. In pre-calculus, we solved vertical motion problems using the position due to gravity, and this is our formula for that. And S sub 0 was our initial position, V sub naught is initial velocity, and our gravitational constant would either be 32 feet per second or 9.81 meters per second, depending on which particular units you were given. In this picture, you can see that the vector here, here's my particle motion, projectile motion, and here's my component on x, and this is our component on y, and there's our velocity vector in that direction. Oh, did I lose it? Okay, so a projectile with some mass m can be launched from an initial position r sub naught, and having an initial velocity v sub naught has a position vector given by this position vector, and you can see how it's related to our pre-calc formula. Likewise, the path of a projectile that's launched from an initial height h has an angle of elevation theta, and we're going to neglect any air resistance, can be described by the vector function given here. So this is our vertical motion, and this is our horizontal motion, and this is our vertical motion. So cosine for x and sine for y. So let's give it a try. At a recent Civil War reenactment, a cannon charge was fired from ground level at a 60-degree angle of elevation and an initial speed of 300 feet per second. And we want to write the parametric equation for the cannonball's trajectory. So we know a couple of things. We know that v sub 0 is 300 feet per second. And we know that r sub 0 is going to be 0 since it's starting on the ground. We also know, since that the units are in feet, that the second derivative is going to be negative 32j. Okay, so that's the vertical direction. We also know that x is 300 cosine 60t, and we know that y is 300 sine of 60 degrees t minus 16t squared, and we got those off of our formula right here. So we got x is v sub naught cosine of theta, and y is v sub naught sine of theta. So using all of that put together, our height was starting on the ground. We had 300 cosine 60 in the horizontal, and we had negative 32, so half of 32 is negative 16t squared, sine 300 sine of 60, and the height started at 0. So putting all that together gave us our parametric equations. Need a little more room here. So our x would be, let's see, cosine of 60, so 150t for the x direction, and our y would be square root of 3 over 2, so 150 radical 3t minus 16t squared. So this was our goal, to write the parametric equations. For part B, the maximum height reached by the cannonball would be the derivative dy dt equals 0. We're looking for that. So this is our y. We're taking the derivative. Y prime is going to be 150 radical 3 over 32. So dy dt, because negative 16t. And if you reduce that down, you could divide out and get 75 radical 3 over 16. So this is when our time, let's see if I'm doing that right, 150 radical 3 minus 32t equals 0. Yes. So y prime equals 0 I didn't write that very clearly here. This is my y prime, and y prime equals 0 when we solve for time at this time. Part C, the horizontal distance that's traveled by the cannonball would be where y is 0 and time is 150 radical 3 minus 16t. I'm taking that equation, the y component, 150 radical 3t minus 16t when that's 0. So we would have time is 0 at 0, and then solving this one, we would have time is 0 when we had 150 radical 3 divided by 16, or 75 radical 3 divided by 8. So this one doesn't really make sense. That's when it starts, and this is when it hits the ground. The speed of the cannonball. Let's see, we need to do that out of the way so we can answer this. The horizontal distance traveled by the cannonball would be the x of 75 radical 3 over 8. So going back to the x coordinate, that was what, 150 times our x value? So 150 times 75 radical 3 over 8. So we need our calculator again. 150 times 75 radical 3 divided by 8, and we have about I'm getting about 2,435.696 feet that the cannonball traveled on the horizontal. This was the time it hit the ground, and this was the horizontal. And then our very last piece says we need the speed of the cannonball at impact. So we know this is impact here, 75. So we got r of t, which was 150 t, and then 150 radical 3 minus 16 t squared. This is our position vector. We needed velocity, the speed at the impact. So the speed would be 150 and then 150 radical 3 minus 32t, and then speed is the square root of the x component squared plus 150 radical 3 minus 32, and then the impact was what? 75 square root of 3 divided by 8. That entire thing squared, all under the radical. So this is our velocity. So the velocity of 75 square roots of 3 over 8, or the speed, I should say. Hopefully it's going to be 300. Let's see. So with our calculator, again, we want the square root of 150 squared plus 150 radical 3 minus 32 times 75 radical 3 divided by 8 squared. And just like I guessed, it was 300 feet per second. Now, how did we know that? Must be magic, of course. The initial velocity, didn't they tell us that? Yes, 300 feet per second. So we should expect that to be the speed at impact as well. And our mathematics proved correct. That's lesson 4. 2 more to go in this unit.